So, thank you for the introduction and thank you for giving me the opportunity to present this work. So, as Hans mentioned, this is a work on modeling of and control of irreversible thermodynamic systems. And it is a joint work with Hector Ramirez from University Santa Maria in Chile that was not able to attend, probably is still sleeping, I would say. A former student of Hector and me, Luis Mora Arac, that finished his thesis in Besançon and that will move to Waterloo in Canada for a postdoc position, and Bernard Maschke from University of Lyon. Okay. So the outline of my presentation is the following. I'm going to start with giving a few words of context and motivation. Then I will give a short summary on boundary control port Hamiltonian systems, and we'll try to explain why it is not able to cope with irreversible thermodynamic systems and why we need a new formulation in order to cope with the first and second law of thermodynamics. It's what we try to do by thinking about these boundary control irreversible port Hamiltonian systems that I'm going to present. And in a second instance, I will give you some first insight on control design using a toy model on the heat equation, a very simple control problem, boundary control of the heat equation. And of course, I will end with some conclusions and perspectives. So just to remind you of what we call port Hamiltonian systems, it's an extension to open physical systems of Hamiltonian and gradient systems. It means that we try to relate the energy of the system with the evolution of the state of the system. So it's not anymore that a way of writing equations by choosing as state variable the energy variables on which we can write balance equation. And the aim of this formulation is to point out a structure behind the equations and use this structure in order to get some results related to analysis of existence of solution and control design. And it has been done in 1992 for finite dimensional systems on the left. And you can see that the Hamiltonian function h of x is related to the dynamics through there's two matrices. One is related to the exchanges of energy within the system, and the other one is related to dissipation. First, this formalism has been proposed for conservative systems, I would say, for the harmonic oscillator, and generalized to a large class of systems, including dissipation. And the important point is that the input and output are chosen such that the product of the input and output is homogeneous to a power in order to make a link between the time derivative of the Hamiltonian and the product of u and y. In the linear case, of course, h of x is a quadratic form such that the derivative of h is linear with respect to the state. In this case also, j of x does not depend on x, and the system is linear. So this formalism has been extended to distributed parameter systems in the same way, but now we do not have any more matrices, but we have differential operators. In this case, J is formally skew differential, and we can have in-domain control using the UD, or boundary control, what is the case when we consider distributed parameter systems. And in this case, the total energy is depending on the product of u and y in the domain and at the boundary. Okay, so in this talk, I will just consider linear distributed parameter systems defined on the one-dimensional domain. And I'm going to show that this formalism can be generalized to cope with irreversible thermodynamic systems, meaning systems for which the thermal domain plays a central role, as it is the case for chemical reactors, diffusion and heat equations and all the I would say, systems defined from smart materials or temperature-dependent systems. And you can see that in this formalism, H is the energy, most of the time, the mechanical and electrical energy, but it does not account for the thermal domain. And the thermal domain is only accounted for through the dissipation. And we would like to have more knowledge about how the energy flows from the mechanical domain, for example, to the thermal one. So this is the aim of this boundary control irreversible Hamiltonian formulation. But in order to get this new formalism, I'm going to recall some basis on boundary control Hamiltonian system, the traditional one that has this form. And I restrict my talk to first order differential operators, meaning that I just have a P1 there, but it could be extended to P2, and most of systems fits into these P1 and P2 cases. Just to say that P1 encompasses, for example, the Timoshenko beam equation, the vibrating string, or the wave equation. And if you want to get the Euler-Bernoulli beam equation, you need to go to the order 2. So the system is defined first without considering any dissipation. This term is only a dissipation in the domain. And from this differential operator, we can parameterize the boundary condition such that if these conditions are satisfied, then we end with this balance equation on the total energy. And we see that from this parameterization of the input and the output, we have this impedance passive formulation, and the dissipation just add a positive term that's do such that the derivative of the energy is decreasing with respect to the dissipation in the domain. And in order to illustrate this formulation on a simple example, okay, I'm going to use an example, but just to say that this formalism has been used for systems described by skew differential operators with or without dissipation for proving existence of solutions or solution, stability analysis, but also for simulation purposes through structure preserving discretization schemes, and for control design, because as the energy is at the core of this formalism, we can modify or try to modify the closed loop energy function by using a controller in order to drive the system to a desired equilibrium position with some given performances. So you can see all these papers that are dealing with these works. And we tried to extend this formalism to deal with parabolic systems, meaning systems driven by diffusion-like equation. And just we obtained first results on proving existence of solution by using closure relation on some extended representation that I'm going to present. But if you did attend the discussion with Hans Wart during the interactive session, probably you heard about this kind of a trick of extending the system and adding some closure relation. So let's consider an example in order to see how this formalism is able to cope with, I would say, the thermal domain. So I'm consider here the 1D isentropic fluid in Lagrangian coordinates, such that my modeling follows the quantity of matter. And in order to represent the equation, the driving equation of this system, I choose as state variables the energy variables, meaning the specific volume of this quantity of matter and the velocity of this quantity of fluid. If I write these two conservation laws, then the time derivative of the volume is associated to the variation in space of the velocity, and the variation of velocity is associated with the variation of pressure. And the total energy of the system is the sum of the kinetic energy and the internal energy of the fluid that is, in this case, expressed from V and phi. And you see that the total energy, the kinetic energy is expressed with respect to one quantity of matter. It's why you do not have the mass in this expression, but the mass is chosen equal to 1. Okay, if you write down this operator, considering the variational derivative of this Hamiltonian, the variational derivative of this Hamiltonian with respect to P and V gives you the velocity minus the pressure, and then you can write down the equation as a first order differential operator, as previously mentioned, with a P1 that is symmetric, meaning that this operator is formally skew symmetric. And if you choose as boundary port variables, boundary input and output, this subset of boundary conditions, you end with this balance equation on the total energy, meaning the variation of H is the product of U and Y. Okay, so it fits perfectly, and we can prove existence of solution, and we can prove that we have a boundary control system, that we have this operator with correct domain, generate a contraction semi-group, etc. Okay, now if we add some viscous damping in this system, the viscous damping is defined from the derivative of tau, and tau itself is defined with the derivative of the velocity. And you can see that in this case, you make appear a second order differential operator that is not anymore formally skew symmetric, that is, now it is related to dissipation. So if you write down equation, you can extend the previous model to this one, meaning that you still have this balance equation, but in the balance equation on the velocity, you make appear this term that is a second order differential operator. And it does not fit anymore in the port Hamiltonian framework. But we can think about a trick in order to recast this system into a port Hamiltonian framework, meaning defined from a skew differential operator, by doing this change of variables, meaning that mu dv over dz now is called ER, and ER is related to FR, and FR is the derivative of the velocity with respect to Z. And we can rewrite this equation, okay, as this system with this closure relation, meaning that ER is related to FR through this relation. It's a kind of feedback on two variables that you define, extended variables you define for this system. Once again, you have a skew differential operator, and you can write balance equation on the energy, and you can derive things on existence of solutions. You can also have the balance equation on H that is related to the input and the output. Yet, this system is now set up from differential algebraic equations, and you see that the thermal domain that is associated to this viscous damping is not explicitly represented. So this approach is quite limited, and we try to extend it including the balance equation on what we call the entropy of the system, meaning that we add an additional variable in order to cope with this thermal domain. This variable is the entropy, and now we can write what we call the Gibbs equation that is associated to the properties of the fluid, that gives you the fact that the variation of the internal energy is related to the variation of the volume with respect to the pressure, and the variation of the entropy with respect to the temperature. So the energy is not now anymore the I would say, the energy that only depends on the velocity and the volume, but the energy also depends on the entropy. So you add a state variable in your definition. From this definition, if you write the conservation of the total energy, you can write the balance equation on the entropy. In this case, the balance equation on the entropy is linked to the square of the derivative of the velocity with respect to z multiplied by mu over t. Okay, so this is an additional balance equation. And you can write down your system of equations on this format, meaning that you still have this first order differential operator, but now the term that is related to the viscous damping is added, and you add an equation related to the entropy balance that relates the other physical domain with the thermal one. And the co-energy variable associated to the entropy is the temperature. And you can see that now this operator looks a bit strange, and it is nonlinear, but it is formally skew-symmetric, meaning that you can recognize that you have the derivative with respect to z of this guy, and on this side you have this guy, that is multiplied by the spatial derivative of this guy. And this operator looks like a skew differential operator. But the interesting point is that now the total energy includes the thermal domain, and it is preserved, meaning that we cope with the first principle of thermodynamics, meaning that the total energy is preserved. So it means that if your system is isolated from the environment, then the time derivative of the energy is zero, because the total energy is preserved. But the nonlinear term just tells that there is a part of the energy that is irreversibly transformed from one physical domain to the other one. And the second point is that from this formalism, we can write the balance equation on the total entropy that makes appear a term there that is always positive, and it is linked to the irreversible entropy production, and it's exactly related to the second principle of thermodynamics, meaning that we have a positive irreversible entropy production. Again, if the system is connected to the environment, then this entropy balance is connected to the entropy flow at the boundary. Okay, so on this simple example, we can see that this new formulation allows to cope with the first and second principle of thermodynamics, and allows us also to include in the balance equation a balance on the entropy and a link with the variational derivative of the energy respect to the entropy, which is the temperature. So it's much more, I would say, complete or sophisticated than the usual port Hamiltonian formulation, for which the thermal domain is just expressed as a dissipation term. So you just say that the part of the energy that is not used in the mechanical or electrical part, it just lost as heat loss. So in this case, you can say that a part of the temperature can go in the matter, for example, in a specific way. So this formulation that we have proposed for this simple example has been generalized for any kind of systems, and it has been accepted for publication in a paper in Chemical Engineering Science that should be published in 2022, but that is available online, for which we redefine the the Hamiltonian of the system as the total energy, not only the mechanical or electrical one, but the one that also include the internal energy and the thermal domain. So the set of state variables is now composed of n components plus one, that is the entropy. So we have n plus one extensive variables of thermodynamics, and associated to this extensive, we have n plus one intensive, so co-energy variables. Okay, and we also define the entropy function as the integral of the entropy over the domain. And we have this nice parametrization. So I say nice, but it can be quite ugly, I would say. But you don't have to be afraid because it's quite generic, but at the end is not so complicated. You can recognize in this equation the state x and the entropy. So this one is a vector, this one is a scalar, and we have the co-state variables and the temperature that is there. This term is related that for the part that does not depend on differential operators, we have the reversible part that is always on the left up corner, there and there. In this case, you can recognize P0 and P1 that we have used for the port Hamiltonian formulations. And then we have these irreversible terms that appears that couple the different physical domain with the thermal one. And the part that is strictly related to the thermal one is there. Okay, so this one is related to the interconnection between, for example, the mechanical domain and the electrical domain with the thermal one. There's two terms. And this one is, for example, when you have heat diffusion or dispersion in a thermodynamic system. Okay, this guy is expressed through this product, and this product is a kind of bracket, but this bracket is locally defined, and it involves the energy and the entropy, and also the structure of the system. And the nice point is that this gamma, as a physical property, it is positive. Okay, so we have these three definitions, and this product are defined like that. So for finite dimensional systems, their product are Poisson brackets, but for infinite dimensional systems, they are only locally defined because in G, you have differential operators. So it means that this product cannot be evaluated over the whole domain, but just locally respect to the space variable. Okay. So the nice point is that it allows to cope with finite dimensional systems, meaning that if P1 and G1 are set to 0, we recover the irreversible port Hamiltonian formulation for finite dimensional systems that are mostly used for nonlinear systems. And you can recognize this P0 and the connection between the temperature and the other physical domains. And if we set G0 and G1 to 0, then we have a PDE system that is similar to the one we have used before, meaning that we have a skew differential, skew symmetric differential operator. And in this case, the balance on the entropy is 0 because the system is power preserving. So it means that there is no irreversible entropy production. So it means that this formulation allows to cope with the previous one, which seems good. And for the moment, I did not discuss the boundary conditions, but from this parametrization, I can also do integration by parts in order to relate the time derivative of the energy respect to the boundary port variables. And again, I can parameterize the input and the output respect to the boundary conditions such that the product of the input and the output is exactly the time derivative of the energy. But now there's effort variables at the boundary are a composition of the traditional one, I mean the one related to the physical domain as the mechanical and electrical ones, but also the one related to the temperature domain, okay? One that is related to the interconnection between the physical domain and one that is purely related to the thermal domain. So this parameterization is the following one. It may appear a bit complicated, but the main difference with the one that we have proposed for a reversible system is that in this case, the underlying matrix can be not full rank. So we have to do some projection in order to have a product that is well defined. So this is why we have this M that is chosen such that M is spanning the columns of this guy that is not full rank in most of cases. Okay, but what you have to keep in mind is that this PE is completely given by the problem, meaning that P1, G1, GS are given by the equation. So once we get this nice parameterization, we can compute M, and from M, we can derive the boundary port variables. Okay, the only condition that we have to satisfy is this one that is quite equivalent to the previous formulation. And with this formalism, we find back that the derivative of the energy is completely defined by the product of input and output, even if you have dissipation, because now we consider the total energy, and from the first principle of thermodynamics, the total energy is preserved. Okay, I don't want to go too much into details because time is running, but it is proven by using the skew symmetry of this operator and the definition of, okay, don't want to go into details, but it's integration by part, and then we split these boundary conditions in order to have this nice property on the product of U and Y. And as mentioned before, when we split this product, this matrix is not full rank, and then we have to use projections that are expressed from MP. But the second nice property is that we can also write the balance equation on the total entropy, meaning that if we write this balance equation, we have that the balance entropy makes appear this term that is positive, and that is linked to the second principle of thermodynamics that tells you that we have an irreversible entropy production. So this is derived from the balance equation on S, that is the last equation of your balance equations. And if you replace it by this expression, from the expression of the product, we make appear a square, and this square is strictly positive and is related to the entropy production, I would say the internal entropy production. And there's three terms are related, one to the cross-coupling between the different physical domains, and one that is only due to the diffusion in the thermal domain. Okay, and from integration by part, we recover that we have balance equation when the system is connected with the environment. Okay, just to come back to the 1D fluid model, if we come back to the expression of the system that I proposed, in this case, then the parameterization, I can recast this equation in the previous formulation by choosing P0 equal to 0, G0 equal to 0, because there is no local terms. P1 is related to this differential operator. G1 is associated to this coupling between the velocity and the thermal domain through the viscous damping. And then we have the driving force that is associated to this viscous damping mu over T. In this case, we have two state variables apart the entropy, and only one is involved in the irreversible process. So we can extend the P. We have this matrix. We can find the M that maps that is spanning the image of this matrix. And we can compute by choosing psi1 and psi2 that satisfy the condition I have given before. We can find back the boundary input and output that fits with the balance equation on the total energy. And you can see that in this case, I can choose as input a combination of the pressure and a term that depends on the viscous damping at one side and at the other side, and the output is the velocity at the other side. And we could have mixed these boundary port variables, and we could also have mixed it in order to recover the scattering input case. So we have all this parameterization that are available. Okay, so I just want to give a word on the heat equation, because I would like to give you some insight on control design on this heat equation. This heat equation is a second order differential operator applied to the temperature. But if you come back to the modeling of this heat equation, is the balance equation on the energy that is associated to the Fick's law, for example, that gives you the flux of energy, the flux of heat in your system. In this case, you only have one state variable because you only have one physical domain. So you only have an entropy balance that is given from the Gibbs equation and the conservation of the total energy that is given there, 1 over T minus 1 over T dot this product. And if you use an integration by parts, you can write this equation. And you can see that in this equation, you have an exact derivative of this term plus a positive term that is related to the irreversible entropy production. In this case, the total energy is the internal energy, and the variational derivative of this total energy is the co-state variable, which is the temperature. And again, it fits perfectly with the formulation we have proposed. But now we have P0, P1, G0, G1 equal to 0, and we just have GS. And you see that we can again define the input and the output in order to cope with the balance equation. In this case, we have the heat flux at the boundary and the temperature as the output. So the natural input and that we have are the heat flux at the boundary of the domain. Okay, now just a word about control design, because this new formulation is quite interesting because it allows to cope with the first and second principle of thermodynamics, and we have a nice parameterization of the input and output that fits perfectly with those two balances. But it does not mean that it simplifies the analysis of existence of solutions, because now my skew differential operators are quite nonlinear and quite ugly, I would say, from the analysis point of view. But the aim is that to see if this knowledge that we add in the way we write equation may be helpful for control design or for analysis in a general sense of the systems. And it's what I'm going to explain on this simple example. It's just a preliminary result on the toy model of the heat equation that I would like to control. So in order to control the heat equation, I'm going to use what we call the availability function. So the aim is to drive the heat equation to a desired equilibrium profile Imagine that you have a bar in which occurs heat equation, and you can control the boundary of your bar. And I just want to consider a simple case. I have an equilibrium profile, and I would like to move this equilibrium profile to a desired one that could be the constant one, but could be also a linear one, that the temperature is not exactly the same along the bar, but that is linear along the bar. And I could also consider more complex systems in which I have one boundary condition that re-inject, for example, heat, such that the system is much more complicated and stable. But the idea is to use the physical consideration in order to do control design. And thermodynamic function that is quite often used for irreversible systems is the thermodynamic availability function. It means that we consider again the energy of the system that is given by this curve, and from the properties of the matter, this curve is always convex. It does not mean that it is strictly convex, but it is always convex from the first and second principle of thermodynamics. And in this, for this potential function, what we are going to define is the equilibrium position we want to reach, that is given by this star, and we define the tangent plane to this curve. And as Lyapunov function, we are going to use the distance between this tangent plane and this curve. And we see that in this case, this distance is strictly convex, meaning that it has a minimum. And the idea is to build a control load such that the control will do such that, this potential function will decrease till this equilibrium position. So this function is built from physical consideration. Okay. And then we can try to express it as a control design problem. So we would like to build output feedback at the boundary such that the open loop system is mapped into a closed loop system that is still an irreversible port Hamiltonian system, but now the driving force that drives the system to the equilibrium is defined from this availability function. And in order to do so, the feedback has to satisfy these two conditions. And these conditions are called matching condition. And we are, in this case, able to solve this matching condition. So we have to do, matching conditions, concern the additional energy that you put in your system and gives you the state, the output feedback that you have to apply to your system. Okay. In this very simple case, these equations are very easy to solve and give you the feedback. Okay. It means that if you do this feedback, you can shape this availability function, and then you have to add some equivalent of damping. In this case, we call it entropy assignment, such that the trajectory converges to this equilibrium position. So one thing is to shape the function, and the other thing is to do such that the trajectory will reach the minimum of this function. And it is done by considering the entropy production. It means that you have to add entropy in your system, and it is related to the positivity of this matrix that you can choose with some degrees of freedom. In the linear case, it leads to very simple control design laws, but you could think about more complex laws for nonlinear systems. Of course, if you want to prove stability, then you have to prove that you have existence of solution, pre-compactness of trajectories, and in order to be able to use the Lassalle's invariance principle or use some convergence arguments in order to show that okay, properly, that you reach exactly the equilibrium, but you have a Lyapunov arguments that gives you that if you have existence of solution, it reaches the equilibrium position. Okay, and we did apply it to the very simple example I mentioned. So we start in the control of a barrel with a given temperature profile, and we try to drive this equilibrium to a desired one that is defined with this linear profile, and applying this availability based interconnection, we see that from the difference of temperatures that we can drive the system to an equilibrium, but we cannot reach the desired position. There is still a bias because we did not inject entropy. But if now we inject entropy, then the difference between the temperature and the temperature profile converges to zero, and then we achieve what we want to achieve. Okay, and it's largely time for conclusion. So in this talk, I try to give some insight in this formulation of irreversible Port-Hamiltonian system that we proposed in order to cope with irreversible systems, but irreversible systems for which the thermal domain play a quite important role, meaning chemical reactors for which chemical reactions depends a lot on the temperature, or heat equation, heat diffusion, all these phenomena that involves temperature. It is also the case for smart materials or microsystems for which the temperature plays a central role. And we proposed a new formulation, a new geometric one that is quite interesting, that makes the link between the boundary conditions and the entropy and energy balances. So it can be used for nonlinear systems. Of course, we do not have all the tools for the analysis in this case, but it gives some insight in the choice of Lyapunov function that could be used for control design, and also insight in the form that the controller may be looked for in order to drive the system to a given position to a desired one. So the extension of this work is, of course, elaboration of control design strategies in a more general setting, but also the extension of this formalism for 2D and 3D systems, and all the analysis that is associated to this new formulation. So I think I have finished my presentation. I thank you very much for your attention, and I'm ready for questions.